Okay, so now here, what is the geometry, or what is the molecular shape for this carbon? What is the molecular shape for this carbon? No.
Bend.
No.
It's a triangle.
Say it loud and proud.
Trigonal planar.
Trigonal planar. This oxygen? No.
That's bent.
This is bent because oxygen always has
Two lone pairs.
2 lone pairs on the top.
How is this supposed to know that's oxygen?
Because I would give you that.
No, I was just saying. I mean, like when you were asking.
Yeah, but I told you it was oxygen though. Okay, now geometry or molecular shape and polarity. Everything now. What did we learn about polarity? How do we classify something as being polar or non-polar?
With the compound.
What about it? Like, how do we know if it's
If it's a higher electronegativity. The one that has a higher electronegativity is what's going to dictate the negative, the partial negative.
right before all of that? Okay. How do we know if something is going to be polar or non-polar?
Is sharing of electrons. Based on sharing of.
No, but even before that, simpler than that.
Electricity.
If it dissociates
Dissolves in polar solvent.
Give me more than that. Give me the general statement for that. How do we know if something? How do we know if something is polar or non-polar? Real general, like real general. Yes. So even more blanket to that. If you have a fungal in there, it's going to be polar. Okay?
But technically, the stuff that we said was not all that though.
Yeah, but y'all not hitting it on the head. Like I'm trying to get y'all to be more
Chemistry
general.
is funny. Sometimes you want it real complex.
Yes.
And sometimes you want it real stupid. How are we supposed to know? That's facts too. That's dead facts.
So all the compounds with funcals in it are polar substance? Is that
Now we're going to change that.
right?
This is what I'm saying. Before I told you, if you see a fungal in there,
It's
you're
polar.
going to think of it as being polar. But now we know that shape has a big effect on what our molecule is going to look like, okay, based on our central atom. Here you have carbon dioxide, all right? Now, carbon dioxide has fungal in it, has 2 funcals as a matter of fact. But how they're situated towards each other,
Opposite end. One.
they're opposite ends, so they're pulling equal and opposite for each other. So each additional pull is canceled out by the other. So while, even though this does have fungal in it and it would have ultimately made it polar, because of the shape and how it's at a linear, it cancels out each other. So now this is now non-polar. You get that? No? Okay. Bet. Bring it home. Okay? So let's take it back home. Okay? What?
I just saw what you did. My
What?
reaction. I saw it.
Alright? So we're on the playground. Okay? We about to play tug of war. You got Skinny Mini Nika. And you got Skinny Mini Keith. Okay? No, you ain't. No, you ain't. Okay? So now, you know how old me? Put this on. Okay? You know, accept yourself, plant yourself for your tug of war.
Can I record you?
Oh, you may not.
She's getting recorded.
I'm getting recorded right here, baby.
Oh, wait, no, you're gonna cut those parts from the
You asked
video.
for a face look.
That doesn't
Huh?
make sense.
What's
Face,
up?
face. Okay? Now again, you plant up yourself. You have, get ready, you know what? I'm gonna get you. Okay? So you have your tug of war ready. What's gonna happen? Skinny Mini Nika against Big Bertha. What's gonna happen? Superman, right? Gonna have me flying. This is how I want you to think about polarity and shape. Okay? Alright, let's go back. Alright, so now here we have oxygen and 2 hydrogens. What's gonna happen? What's on top of oxygen?
2
Pair.
2 lone pairs. So now you have an additional pull of electrons towards this lone pair. So here you have, even though you have, you can think of it as being balanced, it's not, because you have an unequal distribution because of these lone pairs.
Okay, there's a big Bertha.
That's Big Bertha. Okay? So now all the electron density is being pulled up this way. So now your 4 hydrogens are flying. So we're going to have a polar compound. I can't get you. Okay. Alright, so let me have these compounds. We're going to tell polar and non-polar. What's the name of this?
HCl. Hydrochloric acid.
Hydrochloric acid. Polar, non-polar. What's this?
Ammonia.
Ammonia. Polar, non-polar.
Polar. No, polar. It's polar.
Are you sure?
Yeah.
Real sure.
Yes.
Alright. This one.
Polar.
What's the name?
Carbon.
Very good. Polar, non-polar.
Polar.
It's not.
Polar. Polar.
Polar?
Polar.
There. Justify your answer. Why is this polar?
Because there's a fungal in there.
How many funcos are there though?
A lot.
There are 4 of them.
So
should
they
it be
balance.
extra polar?
Okay, then. Let's bring it home again then. Alright? Let's say back in the day. Okay? I have like an image in my head right now. How they used to torture people. They used to like tie them up on the stuff and then pull them. So now, what's gonna happen if I have 4 things pulling on me in equal opposite direction? What's gonna happen? Yeah, we're gonna be dead. We're gonna rip off.
Everything's gonna pull at the same time.
Everything's gonna pull at the same time. So what am I?
Worst thing to think of.
Am I polar, non-polar? If everything is pulling at the same time,
Oh, you're
equal
not
and
getting
opposite.
yo.
We're not getting yours. No, we're not doing that. Okay? So what am I? Non-polar. This is chloromethane. Polar, non-polar.
Do you want us to post this on page?
Post away. Go ahead. I don't mind.
On your page?
Go ahead. I'm cute. Okay.
You gotta do that.
Oh my god.
All right. Here you go. Chloromethane. Polar, non-polar.
Polar.
Polar. Why? Very good. You're being pulled up there. What's the name of this?
Boron tetrafluoride.
Boric acid.
Thank you. Boron trifluoride. Polar, non-polar.
Non-polar.
Non-polar. Good.
Why?
It's not.
Same thing.
It's 3.
3.
You just got one on.
3.
There you go. Okay, you got that one. I'm being pulled. How am I being pulled?
From 3
Three sides.
So that doesn't even out.
How's that not even out? One put under that foot, one put on the right foot, one put
One
behind.
over her neck, like just drink it up.
Do you get it? Good job.
Non-polar.
Non-polar.
Little rest and we're back. So, what's the name here? Sulfur dioxide, polar, non-polar.
Polar.
How do we know?
It's
Polar.
You what?
Yeah,
Hold on. Let me see time.
it's polar.
All right, we got 3 minutes.
Tree?
3.
Okay.
Okay? Are we sure about the fact that sulfur dioxide is, what is it again?
Non-polar.
Non-polar, are you sure?
No.
100%.
No.
Well, I didn't
No.
I bet y'all. I bet. Ooh. Oh, y'all gonna owe me service for the rest
Not
of
me.
the year. I'm
I
talking
said-
about fall semester and all. I'm gonna find y'all.
Not sure.
How exactly do you know if it is polar or non-polar? What must you do beforehand? Draw your Lewis structure. What does your Lewis structure look like for sulfur dioxide?
Oh, it
Have
has
a
an
long
S.
pair
It has a pair on the top,
I
so
know.
polar.
It is polar.
Because again,
Why?
push that to top. Let's get
Did you just tell me the answer? Big.
I told you it's getting draped up in 2 directions. So you
Yeah, but remember though, you got. So tell me draw out the Lewis structure for me.
S in the middle.
S in the middle,
Two on the outside.
O's on the outside.
Double bonds.
Okay, double bond.
Double bonds.
Let's do one bond.
2, plus 3 on 3. And then 2 on the other side. Then why you didn't want?
So, okay, 2 double bonds.
And one there on sulfur.
One over here on sulfur.
It invented.
So this is actually, what family is this in? Trigonal, planar, and the member is? Therefore, we are polar.
So for linear is non-polar.
120.
No, not necessarily, because this is linear and it's polar.
Whatever. I don't remember.
Learn about dipole moments.
Dipole moments, what's a dipole moment?
I don't know.
How do we figure out dipole moments? No?
The bond,
What about the bonds?
the number of electrons.
No.
Oh. The electronegativity.
No. Well, maybe electronegativity. What does electronegativity have to do with dipole?
We'll let you know which one has the greater, well, the charge, the partial charge.
Give me more.
Which way,
To keep going on that line of thought.
I just know which one will be greater, which one can be more.
What do you mean greater? Like that? Those aren't the correct terms that you gotta use. What do we think? Dipole moment is basically the equal or unequal sharing of electrons. That's all it is. If you have a dipole, it means that one of the atoms is more electronegative, so it's going to pull the electron density towards them. So therefore, you have a greater electron density on one side of your molecule. Therefore, that gives you a dipole. What else? What else have we learned?
So I have a quick question. Final exam on the 10th?
No final exam. We got to finish our chapters first before you get there. Anything else, or we want to just jump right in? Jump right in? All right.
You should recap.
So, are we going to finish these questions? We had, the first one was what? If it's, we want to predict if it's polar or non-polar. Polar. First one,
Polar.
polar. Second one,
Sulfur, no polar.
Non-polar.
you're going back with the non-polar foolishness.
The
Oh,
polar.
Polar. Here.
Yeah, how you trigonal planar. So if that's trigonal planar, this whole molecule will be bent. And therefore, you have an unequal sharing of electrons. So that is polar. What's the name of this?
Sulfur hexafluoride.
Sulfur hexafluoride.
Non-polar.
Nonpolar, polar.
Non-polar.
Nonpolar. What's the name of this?
Nitrogen trifluoride.
Nitrogen trifluoride, polar, nonpolar.
Nitrogen. No, polar.
How you figure that?
One lone pair.
There you go. Nitrogen has a lone pair, so it's going to be polar. What's the name of this?
Bromine, chlorine,
No.
tetrachloride, trichloride.
What? No. B is not bromine.
Boron.
Boron trichloride, and it's nonpolar. Alright? So, switching gears a little bit, we're going into covalent bonding and orbital overlap. We have the valence bond theory. All the valence bond theory is telling us that our valence electrons are what actually does our bonding. Okay? So now let's see. Which orbital is our valence electron in for hydrogen? Which orbital is our valence electron in for hydrogen?
S.
1s. What does the s orbital look like? Big squishy ball, right? So now, when two s orbitals come together to overlap to make a bond, what do they look like? They, not necessarily Mr. Peanut, but they overlap together, right? Now, let's say if you have hydrochloric acid, which orbital does your chlorine valence electrons come in?
Chlorine
Chlorine comes in with P. So what does the P orbital look like? Mr. Peanut. So if you have a hydrogen and a chlorine coming together to overlap, you're going to have a big squishy ball bonding with Mr. Peanut. Okay? Now, if you have a chlorine-chlorine single bond, you're going to have two p orbitals coming together and overlap. Right? So this is what these things look like. Here you have two s orbitals coming together to overlap. Here you have an s and a p. Here you have two p's. Now, your p orbitals can overlap in two ways. I mean, we'll get to explain exactly what they mean, because the two ways they overlap gives you something different. This one is called a head-to-head overlap. So the electron density will be in between the two nuclei. The next way it can overlap, the p orbitals can overlap, is side to side.
Side to side.
Side to side. No, this is top and top. This is head to head. Head to head, and then you have side to side. When you have side to side overlap, you have the electron density above and below your internuclear axis.
So it's shear, like all over, everywhere.
No, not everywhere, just above and below. Okay? Now here, the same thing goes with what we're talking about with balancing the attractiveness and repulsiveness of your electron density cloud. Here, there's an optimal overlap in order to get your bond. When you are, in terms of how the potential energy will be, if you have the electron density coming close to each other, what's going to happen? Electron density. If they come close to each other, what's going to happen? They're going to repel each other. Alright? If they repel each other, what's the potential energy going to be? Is it going to be high? Is it going to be low? It's going to be high. The closer they are together, you're going to increase your potential energy. The further they are, they're going to decrease the potential energy. But there's an optimal distance that you can get based on your dipoles and your London dispersion forces that will get you your bond. what group is beryllium in? 2. How many bonds can it make?
2.
2. Okay? So now draw me the orbital diagram for beryllium. When we say orbital diagram, what are we talking about? The box is very good. So what do we have? What's the name of our first box?
1s,
1s. How many rooms?
2,
1 room.
1,
1 room, 2 electrons. Next box.
2s, 1 box,
How many?
2 electron,
Next box.
2p,
How many? What's it called?
2p,
2p. How many boxes in here?
3 boxes, 6 electrons.
How many electrons do you have here for beryllium?
1 is 2, 2 is 2.
None, right? Good. So now, what exactly do you need in order to form a bond? You need an electron, right? You need an unpaired electron that is ready to accept an electron from your other atom, right? As beryllium is right now, can it make a bond?
No,
Why is that?
because this has a couple bonds like this.
There you go. You have a doubly occupied highest molecular atomic orbital. All right. So you have no free electrons. So what exactly do you think you can do?
Make 1 electron to heat.
There you go. You can promote 1 electron to your 2p. If you do that,
So that's mean when beryllium do the reaction, as they transfer the electron, then give up the 2 electrons from 1s, from 2s1 and 2p1, right?
right.
The beryllium 2 plus.
Yes. Okay. So you have just promoted one of your 2s electrons to your 2p. So this now is no longer a 2s electron. You have just made a hybrid. So you still have your 1s. Now you end up with how many of your s orbitals did you take?
1.
1. How many of your p orbitals did you take?
1.
1. So you end up with a mixture of these 2 orbitals and you make it an sp orbital.
Oh. 1.
Okay, so here you've promoted it. Your sp hybridized orbitals, you're now mixing these 2 orbitals in order to allow you to have a bond.
So you cut down 1 box from 2p and add it to 2.
Yes. So you took 1 orbital from your 2p and you took your 2s and you mixed them together to make your
sp hybrid.
sp hybrid orbitals. Okay? Your sp hybrid orbitals is a combination of your 2s and one of your 2p orbitals, and they're going to be slightly bigger than that of your p orbital, but they're the same shape. All right? So here is what you end up with, and this is what we have. This is our hybrid orbital for beryllium. All right? So here, if you now take, what's the name of this?
Beryllium chloride.
Beryllium,
Dichloride. Chloride.
beryllium fluoride. Beryllium is still a metal. Right? If you take beryllium fluoride and you're making this bond, you end up with what kind of family? What family is this? You end up with linear. So you know that an sp orbital will have a linear family. Alright?
So sp has linear family.
Yes. So now, if we now take boron, what is the orbital diagram for boron?
2p1,
So we have 2s,
2s2,
2s2,
2p1.
2p1. How many bonds can boron make? 3D. 3. So now what do we have to do? Can it make 3 bonds as it is right now?
No, only one bond.
So what can it do?
Transfer 1, 2s2.
You're going to promote another electron. So if you promote another electron, what would be your hybrid orbital now?
Then sp. 2 sp2.
sp2. So what that means, you've taken one of your s orbitals and 2 of your p orbitals, and you're now going to, you mix them and you make 3 degenerate orbitals, which has the configuration of sp2, the hybridization of sp2. What family does this look like? Trigonoplanar. All right. Now, what about carbon?
Carbon is 1s2, 2s2.
1s2,
2s2,
2s2, 2p, 2p2. How many bonds can carbon make?
2, 4.
4. All right. So can it make 4 bonds here?
No, only 2 bonds.
So what can you do?
Transfer 1s2, 2s2.
You're going to promote 1 electron up to your 2p. So now you've mixed all of your p's
So you know it's
with your s. So now what is the hybrid orbital designation? sp,
3.
sp3. Alright? So with carbon you have 4 degenerate orbitals, which takes up the name for sp3, and you have your mixing of all of these together to make your, which is your, what's the family here? Tetrahedral. Very good. Do we get that? Alright. So I have summarized all of what we just learned. These are the major points. Okay? If you have an sp hybridized orbitals, this is how you recognize them. You will have all single bonds. If you have a single bond is also called, excuse me, a sigma bond. If you have an sp2 hybridized orbital, you have a double bond around your central atom. A double bond is a mixture of 1 pi bond, and I'll show you what a pi bond is in a second, and 1 sigma bond. You have an sp hybridized orbitals. Here you have a triple bond. With a triple bond, you have 1 sigma bond and 2 pi bonds. So again, all of these things we've seen before. Here you have your single bond. Your single bond is also called your sigma bond. Your double bond contains 1 sigma bond and 1 pi bond. In a triple bond, you have 1 sigma bond, 2 pi bonds.
What's the pi bond you said?
Oh, we'll get to it in 2 slides.
Like in here you say hydrogen is sigma bond.
Sigma bond.
So, but hydrogen has a p orbital.
No, it doesn't.
So how is it sp3?
Hydrogen is not sp3. Carbon is sp3. If you see all single bonds around your central atom, that's sp3 hybridized.
Okay.
Alright, so here we go. Indicate the geometry, meaning the family and the member, and the orbital hybridization of the following that's around the central atom. So what's the first thing we do? Trying to figure out the family and the member. Lewis structure. So draw the Lewis structure. So what do we have? Tell me what to draw.
Nitrogen
Nitrogen,
and two single bonds.
hydrogens,
One
bond.
single and one
And
bond
two
here.
lone pairs on nitrogen.
Two bonds here.
what's the family?
It's bent and
And that's not the family.
trigonal
The,
bent.
Tetrahedral,
Bent.
you have four things around the central atom, and the member is bent because you have two lone pairs, two bonded pairs. You have to know this, guys. Okay? So what's a hybridization? sp3. So what's the name of this? Sulfite. Good. What is the family? What's the member? What do I draw?
S in the middle.
S in the middle.
3 single bonded O.
3 single bonds with oxygen. One lone pair on sulfur.
And 3 lone pair each oxygen.
3 lone pair on each oxygen. Is that it? So, what's the family?
Tetrahedral.
What's the member?
Trigonopyramidal.
And what's the hybridization?
P3.
That's what I got to. Okay? Alright. Now here you go. Sigma bond. When you have p orbitals that's doing your bonding, you can have two types of overlap. You have a head-to-head overlap. If you have a head-to-head overlap, you're going to get something that looks like a sigma bond. So remember what we did for hydrogen. Hydrogen gas comes together looking made from 2s orbitals. When they overlap, the electron density is in between the internuclear axis. This gives you a sigma bond. When you have an S and a P coming together, you have the electron density in between the internuclear axis, the two nuclei. That gives you a sigma bond. Alright? So when you have two p orbitals coming together, you will also have something that looks like a sigma bond. When you have this head-to-head overlap. You can also have side-to-side overlap. Your side-to-side overlap gives you your electron density above and below the internuclear axis. That now gives you a pi bond. This is a pi bond. Do we get that?